Keeper 7.5, long division and partial fractions. All right, so we use polynomial long division when you have a rational function where the degree of the numerator is greater than or equal to the degree of the denominator. All right, so like the degree of the denominator is smaller than that of the numerator or equal to the numerator. You can either use long division or synthetic division depending on what your denominator looks like before you integrate. All right, so here's our steps from Algebra 2. If you guys, some people might have seen this in Algebra 2, some may not have, but here's the steps that you should have learned in Algebra 2 for polynomial long division. All right, so make sure your polynomial is written in standard form, so it's in decreasing order. Then you want to do your division, so you divide the term with the highest power inside the division symbol by the term with the highest power on the outside of the division symbol. After you divide, then you multiply whatever you got, whatever answer you obtained from that previous step. Then you want to subtract and bring down the next term. And then you just keep repeating that steps until you can't bring down any other terms. Then you just want to write your final answer. And just remember that whatever your remainder is, you divide that by the original piece that you were dividing by to start. All right, so here's our example. We have the integral of x squared over x plus 1 dx. Now, if you notice, the degree of the denominator is 1, and the degree of your numerator is 2, so the denominator is smaller than the numerator. That means I can divide that into it. I can divide the denominator into the numerator. And so I'm going to set up my long division, or I could do synthetic, but I'm just do long because most people forget how to do long division. So I'm going to set up my long division. And I'm going to do x plus 1 on the outside, and on the inside I'm going to have my x squared. But I'm also going to put some placeholders for the x in the constant term just so that I don't confuse myself later. All right, so what you want to do is you want to ask yourself, you want to look at the highest term on the outside, which is our x, and you want to look at the highest term on the inside, which is x squared, and you want to ask yourself, what do I need to multiply times x that would give me x squared? Well, we know that x times x equals x squared, so I'm going to multiply by x. All right, now once you get that x, you're going to multiply this x that you got by each term outside of your division bar. So this is going to be multiplied times that, and this is going to be multiplied times this. And so I'm going to have x squared plus 1x. So from there, you subtract the two values, so I'm subtracting x squared minus x squared, and I'm subtracting 0x minus 1x. And so when I do that, I'm left with negative x, and then I bring down the 0. So negative x plus 0. So you want to ask yourself again, what do I do to this x to get negative x? Well, you should recognize that if you multiply x times negative 1, you'll get negative x. So I put negative 1 in my numerator. All right, then I take that negative 1, and again, I multiply it out. So I'm just repeating the same steps. So I multiply it by both terms, and I get negative x minus 1. Once I multiply that out, I subtract. And by subtracting, that's going to change all of these signs. So that's going to become plus, and that's going to become plus. And so when I subtract, I should get a remainder of 1. All right, so what I'm going to do is I'm going to rewrite this original integral as what I just found using my long division. So instead of the integral of x squared over x plus 1, I'm going to do the integral of x minus 1 plus 1 over x plus 1. So again, x minus 1 came from here, and then the 1 over what we were originally divided by is how I got this piece over here. All right, so now I can take this integral very, very simply. I know the integral of x is x squared over 2. The integral of negative 1 is x. And the integral of 1 over x plus 1 is simply u substitution. So I'm going to do u equals x plus 1. Du is dx. So I'm going to be left with my integral of x squared over 2 minus x plus the integral of 1 over u du, which we know is ln of absolute value of u. So I have x squared over 2 minus x plus ln absolute value of u plus c. And then you guys know we can't have the u in our expression, so we take that out and substitute it back in for x plus 1. All right, so next example, I notice here that the degree of my numerator is 1 and the degree of my denominator is also 1. So since they're the same, I could do, again, either long division or synthetic division to simplify this. Again, I'm going to do long division because I think that a lot of times you'll end up with a lot of times you won't have just a linear factor, and so you really need to be comfortable with doing your long division. So setting up my long division, I have x plus 2 on the outside, and then x plus 0, 0 as the placeholder on the inside. And so, again, I'm going to ask myself, well, what do I do to this x on the outside to obtain this x on the inside? Well, it's exactly the same, so technically that means I simply multiplied by 1. And so I put 1 on top. Then when I have the 1 on top, I'm going to multiply this back through. So 1 times x, and then 1 times 2. And so I get x plus 2. And then we subtract. And remember, by subtracting, you're changing your sign, so that becomes negative, and this also becomes negative. And so we have, or we're left with, negative 2. All right, so I'm going to rewrite my integral as 1, which was what we got when we divided, minus 2 over x plus 2, which was my remainder. Now integrating this, I get x minus 2 integral 1 over x plus 2. Doing a quick u sub, I get u equals x plus 2. That means du is dx. And I'm left with x minus 2 integral 1 over u du. And then I should be able to quickly see that that's just ln absolute value of u. So I have x minus 2 ln absolute value of u plus c. And then plugging my u back in, I have x minus 2 ln x plus 2 plus c. All right, so next one, and I'm going to go a little bit faster on this one just so you can see how I would do it in actual time, or what I would actually write down. I have the integral of x cubed minus 2x plus 5 over x minus 2. Again, the degree of my numerator is 3, and the degree of my denominator is 1, and so my denominator is less than my numerator, so I'm going to divide. Now this time I'm going to do it the quicker way because, again, this is how I would actually do it in real life. Because my denominator is a linear factor, I can actually just use synthetic division. And so if you remember with synthetic division, you're going to take the 0 from your denominator, which is 2. You're going to put that on the outside of your bar. And then you're going to do the coefficients of your numerator on the inside, making sure to include any placeholders. So I have 1, 0 as a placeholder, negative 2, and 5. Those are my coefficients of my numerator. Now, following my rules for synthetic division, this first one right here, I simply just drop down, and then we multiply 2 times 1, which is 2. Then we add 0 plus 2 is 2. Then we multiply to get 4. Then we add to get 2. We multiply to get 4, and then we add to get 9. And so what that tells us is that our division would yield x squared plus 2x plus 2 plus 9 over x minus 2. The key to this is remembering that whatever you started with, so we started with a cubic, your division is going to be 1 less, so that's how I knew my division started with a quadratic. And remember, this last number is always your remainder, and you divide that by what you originally were dividing by. All right, so now we have the integral of all that, so the integral of x squared plus 2x plus 2 plus 9 over x minus 2 dx, and I'm going to take my integral to get x cubed over 3 plus x squared plus 2x plus 9 ln x minus 2. And that 9 ln x minus 2, again, comes from a u sub, but you should by now see that when you do this u sub, because there was nothing in front of the x here, your du is just going to be your dx, and you'll just have 1 over u, which would be ln of u, which was ln of x minus 2. So you don't have to show the u sub when there's simple ln functions like this. You could just write out your final answer. All right, so the next thing we're going to talk about is our partial fraction decomposition. And we use this when I can't divide. And sometimes I can divide, but then what I'm left with, I still can't solve and I still can't divide. So you want to use partial fractions when you can't divide, but your denominator is factorable. So if your denominator is factorable, you want to try to go this route. All right, so here's your algebra 2 steps for partial fraction decomposition. Again, if you saw it in algebra 2. So you want to set up your partial fraction using constants a, b, and c in your numerator. You basically want to get a common denominator. Then you want to simplify your expression. And then what you're going to do is you're going to kind of do like a matching game where you set your powers or your coefficients of the powers equal to each other. You're going to solve for A, B, and C, usually using some sort of system of equations like substitution, elimination, something like that. And then you'll substitute that back into the original integral. All right, now we have different setups depending on what our factors are. If your factors are distinct linear factors, so they're different, right? Like x plus 2 and x plus 3, or 5x minus 7 and 2x plus 3, something like that. If they're distinct linear factors, you simply do a over the first factor plus b over the second factor. If they're repeated factors, so repeated linear factors like x plus 2 squared, you're going to do a over x plus whatever it is, like x plus 2, and then b over that thing squared. Okay, so again, if they're repeated factors, you're going to do a over one of them and then a over 2 or b over 2 of them. Now, if they're linear and repeated, so you have a combination of the first two that we talked about, you're going to do a over the first factor, b over the second factor with just to the first power, and c over the second factor, but to the second power. And then the last one, if you have a linear and a quadratic, so like you have a linear factor of ax plus b and then a quadratic, some kind of squared factor, you're going to do a over the first factor plus bx plus c over the second factor. All right, so our next example, we have the integral of 5x minus 4 over 2x squared plus x minus 1. Notice we cannot do long division here for the simple fact that my denominator's degree is greater than that of the numerator. So I'm going to try to factor my denominator. And so step 1, factor my denominator, I get 2x minus 1 times x plus 1. And so I'm going to set up my partial fraction decomposition, and since they're distinct linear factors, I'm going to do a over the first factor plus b over the second factor. From here, I'm going to try to get a common denominator. And so I'm going to take this x plus 1 and I'm going to multiply it on the top and the bottom of the a side. And then I'm going to take this 2x minus 1 and multiply it on the top and the bottom of my b side. All right, so when I do that, I'm going to get ax plus a plus 2bx minus b all over my common denominator. Now, what you want to realize is that this denominator is the same as the original expression. So this 2x squared plus x minus 1 is the same as the original, which means that the numerator of ax plus a plus 2bx minus b has to be, if these are equivalent, has to be 5x minus 4. So what I'm going to do is I'm going to set those numerators equal to each other. And so ax plus a plus 2bx minus b equals 5x minus 4. And then I'm going to set like terms equal to each other. So in other words, I have a ax here and I have a 2bx here. They both have x's. That must equal my 5x. And then my a, which is just a constant, and my negative b is a constant, it must equal the constant on the other side of negative 4. So I have, again, ax plus 2bx has to equal 5x, which means that a plus 2b has to equal 5, and then a minus b has to equal negative 4. Now I'm going to solve that system of equations. So again, a plus 2b equals 5, and a minus b equals negative 4. If I subtract these two equations, so again, just being thorough, I'm going to subtract the top equation from the bottom equation, and I'd be left with 3b equals 9. And then I can divide both sides by 3 to get b equals 3. Now, if b equals 3, I can take that and plug it into any one of my equations. I'm going to plug it into the easier one, or the one that has less work. And so I get a minus 3 equals negative 4, or a equals negative 1. And so now that I know a and b, I can rewrite that back into my original partial fraction setup. All right, so I'm going to take the a, I'm plugging in here for this a over here on step 2. I'm going to take b and plug it in here, and I'm going to write that into my integral. So I have -1, that was my a, over 2x minus 1, plus 3, which is my b, over x plus 1 dx. Now doing each integral separately or breaking it up, I have negative integral 1 over 2x minus 1 dx plus 3 integral 1 plus x plus 1 dx. Doing a u sub for each one of these, I would have u for the first one is 2x minus 1, and u in the second one would be x plus 1. Du would be in the first one 2 dx, or du over 2 is dx, and then in the second one du is just dx. And so plugging in those u substitutions, I get -1/2 integral 1 over u du plus 3 integral 1 over u du. And so then integrating those, I get ln on both of them, with the -1/2 in front of the first one and 3 in front of the second one. And then plugging those u's back in, I get -1/2 ln 2x minus 1 plus 3 ln x plus 1 plus c. Final answer. All right, so next example, again, I have to do partial fraction decomposition because my denominator is bigger. So first thing I'm going to do is factor it out to be x plus 4 and x minus 1. Since they're distinct linear factors, I'm going to set a over x plus 4 and b over x minus 1. Please understand, though, it doesn't matter which one is over which one. It doesn't matter. You could switch it and do like a over x minus 1 and then b over x plus 4. It's totally up to you. Then I'm going to get a common denominator, so I'm going to multiply this a side by the x minus 1, and I'll multiply the b side, so this piece, by the x plus 4. And so I'm going to have ax minus a plus bx plus 4b, and again, that's just the numerator, so I know that numerator has to equal the numerator of my original, which was 2. Now setting my like terms together, I'm going to have a plus b equals 0, so those are my x terms. So ax plus bx equals no x on this side, so a plus b equals 0. And then my constants of -a plus 4b has to equal 2. Now solving that system of equation by adding the two equations together, the a's are going to cancel out. I have b plus 4b, which is 5b, and then 0 plus 2 is 2. So b has to be 2/5. Now if b is 2/5, by default a has to be -2/5 because a plus b in this equation had to equal 0. So a is -2/5. Now plugging that back in for a and b and integrating, I get 2/5 over x minus 1, and I switched the order so that the positive was first, minus 2/5 over x plus 4 dx. Again, doing a quick integral on this, I know that because the x has no coefficient on it, I know it's just going to be ln of that. And so I get 2/5 ln absolute value of x minus 1 minus 2/5 ln x plus 4 plus c. All right, so last example, we have the integral of x squared minus x plus 1 over x squared plus x. First thing I notice is that my degrees are the same on the top and the bottom, which means I can do long division first. So setting up my long division and putting in my placeholders, I'm going to ask myself, what do I do to x squared to get x squared? And we should know that multiplying by 1 will give us x squared. So I put 1 on top. I'm going to multiply that back out to get x squared minus x plus 0. And then I'm going to subtract, and I'm going to end up with -2x plus 1 as for a remainder. And I know that's a remainder because there's nothing I can do to x squared to give me -2x. So now rewriting that as my integral, I have integral of 1 plus my remainder over the original thing I was dividing by. So 1 plus -2x plus 1 over x squared plus x. Now what I notice is this part that I have colored in blue, I still can't integrate. And so I'm going to have to do partial fraction of that piece. And so what I'm going to do is I'm going to focus on that denominator and I'm going to factor it out. So x squared plus x equals x times x plus 1. Those are distinct linear factors, so I'm going to say a over x plus b over x plus 1. I'm going to get a common denominator by multiplying a times x plus 1 and then b times x. And I'm going to set that equal to my numerator of -2x plus 1. This means that a plus b are my x terms, so ax plus bx has to equal negative 2x, or a plus b equals negative 2. And then we have our constants, which is a on the left, has to equal 1 on the right. Well, if I know that a equals 1, b must equal negative 3, because if I put 1 into this equation here where I'm highlighting and then subtracting on both sides, I get b equals negative 3. Now plugging that a and my b back into my expression and back into my integral, I have the integral of 1 plus 1 over x for a minus 3, that was our b, over x plus 1. Now integrating that quickly, I'd have x plus ln absolute value of x minus 3 ln x absolute value of x plus 1 plus c.